Hello dear students. So after the coding process, the next important activity in software development life cycle is testing of the program. Testing is intended to show that a program does what it is intended to do and to discover program defects before it is put into use. The engineer creates a series of test cases that are intended to demolish the software that has been built. In fact, testing is the one step in the software process that could be viewed, at least psychologically, as destructive rather than constructive. Testing objective. Glenn Myers states a number of rules that can serve well as testing objectives. Testing is a process of executing a program with the intent of finding an error. A good test case is one that has high probability of ending an yet undiscovered error. A successful test is one that uncovers as yet undiscovered error. So the primary testing objective is to design tests that systematically uncover different classes of errors and to do so with minimum amount of time and effort. Testing principles. Before applying methods to design effective test cases, a software engineer must understand the basic principles that guide software testing. Davis suggests a set of testing principles that have been adapted. 1. All tests should be traceable to customer requirements. As the objective of software testing is to uncover errors, it follows that the most severe defects from the customer's point of view are those that cause the program to fail to meet its requirements. The test should be planned long before testing begins. Test planning can begin as soon as the requirements model is complete. The Pareto principle applies to software testing. Stated simply, the Pareto principle implies that 80% of all errors uncovered during testing will likely be traceable to 20% of all program components. The problem, of course, is to isolate these suspect components and to thoroughly test them. Testing should begin in the small and progress towards testing in the large. The first test planned and executed generally focus on individual components. Exhaustive testing is not possible. The number of path permutations for even a moderately sized program is exceptionally large. It is impossible to execute every combination of paths during testing. To be most effective, testing should be conducted by an independent third party. By most effective, we mean testing that has the highest probability of finding errors. Pareto principle. The Pareto principle is a principle named after economist Vilfredo Pareto that specifies an unequal relationship between inputs and outputs, also known as 80/20 rule, the law of the vital law, or the principle of factor sparsity. Pareto principle states that for many events, roughly 80% of the effects come from 20% of the causes. In software engineering, Lowell Arthur expressed a corollary principle. 20% of the code has 80% of the errors. Find them and fix them. Microsoft noted that by fixing the top 20% of the most reported bugs, 80% of the related errors and crashes in the given system would be eliminated. This is Pareto principle. What are the attributes of good tests? Keiner, Fogg, and Neogin suggest the following attributes of a good test. 1. A good test has a high probability of finding an error. To achieve this goal, the tester must understand the software and attempt to develop a mental picture of how the software might fail. Ideally, the classes of failure are probed. For example, one class of a potential failure in the graphical user interface is a failure to recognize proper mouse position. A set of tests would be designed to exercise the mouse in an attempt to demonstrate an error in mouse position recognition. 2. A good test is not redundant. Testing time and resources are limited. There is no point in conducting a test that has the same purpose as another test. Every test should have a different purpose. 3. A good test should be best of breed. In a group of tests that have a similar intent, time, and resource limitations may mitigate towards the execution of only a subset of these tests. In such cases, the test that has the highest likelihood of uncovering a whole class of errors should be used. 4. A good test should be neither too simple nor too complex. Although it is sometimes possible to combine a series of tests into one test case, the possible side effects associated with this approach may mask errors. In general, each test should be executed separately. Two types of testing processes are validation testing and defect testing. Validation testing to demonstrate to the developer and the system customer that the software meets its requirements. A successful test shows that the system operates as intended. Defect testing to discover faults or defects in the software where its behavior is incorrect or not in conformance with its design specification. Actually, the difference between validation testing and defect testing is that in validation testing is done on the final testable system or module or build to ascertain whether it complies with the requirements as stated by the stakeholders or the client, whereas defect testing is the testing of the software module or system or the build to find potential or hidden defects that may or may not hamper the system. These defects could range from functional, user interface, integration, etc. Another two testing terms are component testing and system testing. We should learn what is the difference between this component testing and system testing. Component testing is the testing of individual program components. Usually, the responsibility of the component developer is component testing. Tests are derived from the developer's experience. Whereas in system testing, testing of groups of components integrated to create a system or subsystem. is performed. The responsibility of an independent testing team exists. Tests are based on a system specification. Now, the testing process can be represented with a diagram like this. This testing process involves four processing activities. First processing activity is the design of test cases. Second activity is preparing the test data. Third activity is running the program with this test data. And fourth activity is comparing the results of these test cases. To perform the design of test cases, the first step is identifying the test environment. Identify the physical test environment and the production environment, which includes the hardware, software, and network configurations. Having a thorough understanding of the entire test environment at the outset enables more efficient test design and planning. As a result of this design of test cases, various test cases can be generated as the output of the design test case activity. Based on this design of these test cases, the test data is prepared. Two kinds of data can be prepared. One is the data during the execution, the expected result. Second one is the real result, actual result that we are supposed to attain. In the final stage of processing activities of the comparing results, these two test cases values are compared and the test report is generated. So after preparing the test data, using the test data, the third activity of running the program with test data is performed, and the test results are collected as the result of running the program with test data. And finally, the results of this test and the real results that is expected is compared, and thus the testing process is performed. The steps described here are simply a guideline, and each application will have unique needs and challenges to face when testing. However, the general picture is like this. Software Testing Life Cycle (STLC) identifies what test activities to carry out and when to accomplish those test activities. Even though testing differs between organizations, there is a testing life cycle. STLC starts as soon as requirements are defined or SRS document is shared by stakeholders. STLC provides a step-by-step process to ensure quality of the building software. The various activities of the testing process, like designing the test cases, preparing the test data, running the program with test data, and comparison of the results with the test cases, is performed based on these software testing life cycle stages. So, when we begin the software development activity through system engineering, requirement, design, and code activity, we are reaching from abstract to concrete level in the software design activities. In software development activities. In all these different levels like system engineering, requirements, design, and code, from abstract to concrete level, different levels of testing is possible. Unit testing concentrates on each component or function of the software as implemented in the source code. Integration testing focuses on the design and construction of the software architecture. Validation testing requirements are validated against the constructed software, and system testing the software and other system elements are tested as a whole. That is, a narrow to broader scope of testing is performed from unit testing to system testing through unit testing, integration testing, validation testing, and system testing activities. Now we are going to discuss how test case design can be done. Any product or system can be tested on two ways. The two ways can be categorized as black box testing ways and white box testing method. Now let us discuss what is black box testing. Black box testing is knowing the specified function that a product has been designed to perform. Tests can be conducted that demonstrate each function is fully operational while at the same time searching for errors in each function. That is, black box tests are used to demonstrate that software functions are operational, that input is properly accepted and output is correctly produced, and that the integrity of external information, example a database, is maintained. A black box test examines some fundamental aspects of a system with little regard for the internal logical structure of the software. Now, white box testing, knowing the internal working of a product, tests can be conducted to ensure that all gas mesh, that is, internal operations, are performed according to specifications and all internal components have been effectively exercised. That is, software is predicted on close examination of procedural detail. Logical paths through the software are tested by providing test cases that exercise specific sets of conditions and or loops. The status of the program may be examined at various points to determine if the expected or asserted status corresponds to the actual status. This is white box testing. So, white box testing, sometimes called glass box testing, is a test case design method that uses the control structure of procedural design to derive test cases. Logical paths through the software are tested. The status of the program may be examined at various points, and it uses the control structures of the procedural design to derive test cases. So, using white box testing methods, the software engineer can derive test cases that guarantees that all independent paths within a module have been exercised at least once. 2. Exercise all logical decisions on their true and false sides. 3. Execute all loops at their boundaries and within their operational bounds. And 4th, exercise internal data structures to ensure their validity. The problem or constraints with white box testing involves it does not find missing or additional functionality. Also, it does not really check the interface in the components, among the components, and it is difficult for large and complex modules to check the various testing activities. The advantages of white box testing involves it helps optimization of the code, it helps for the removing extra lines of code. All possible code pathways can be tested, including error handling, resource dependencies, and additional internal code logic flow. Enables tester to find programming errors quickly, and good quality of coding work and coding standards can be performed with this white box testing activity. The disadvantage of white box testing: a deep knowledge of code and internal structure is a prerequisite. A skilled tester is needed to carry out this type of testing, which increases the cost for the testing activity. It is impossible to look into every bit of code to find out hidden errors. It is very expensive technique, and it requires knowledge of the target system, testing tools, and coding language. So whitebox testing requires specialized tools such as source code analyzer, debugger, and fault injectors for the successful testing activities through the whitebox processing, which is expensive and time consuming. That is a major disadvantage for this whitebox testing. So let us understand different types of whitebox testing. Four types of whitebox testings are basis path testing, graph matrix, control structure testing, and data flow testing. Tom McCabe proposed basis path testing. Basis path testing is a white box testing technique. When we write the program or code, basis path testing can be used to derive the logical complexity measure. Test cases derived to exercise the basis set are guaranteed to execute every statement in the program at least one time. We had discussed basis path testing when we discussed about complexity metric of a program. So various methods for deriving test cases are flow graph notation, cyclomatic complexity, deriving test cases, and graph matrices. Before we consider the basis path method, a simple notation for the representation of control flow called flow graph or program graph must be introduced. The flow graph depicts logical control flow using the notation shown in the first row of the figure. For each flow graph symbol, the corresponding structured construct is shown in the below part of this slide. To illustrate the use of a flow graph, consider the procedural design represented in this left side of this figure, that is figure A. Here, a flow chart is used to depict program control structure, figure B, that maps the flow chart into a corresponding flow graph. We assume that no compound conditions are contained in the decision diamonds of the flowchart. Referring to figure B, each circle called a flow graph node represents one or more procedural statements, a sequence of process boxes, and a decision diamond can map into a single node. The arrows on the flow graph, called edges or links, represent flow of control and are analogous to flowchart arrows. An edge must terminate at a node even if the node does not represent any procedural statements. Areas bounded by edges and nodes are called regions. When counting regions, we include the area outside the graph as a region. When compound conditions are encountered in procedural design, flow graph becomes slightly more complicated. In this figure, the program design language PDL segment translates into the flow graph is shown. Note that a separate node is created for each of the conditions A and B in the statement if A or B. Each node that contains a condition is called a predicate node and is characterized by two or more edges emanating from it. An independent path is any path through the program that introduces at least one new set of processing statements or a new condition. When stated in terms of a flow graph, an independent path must move along at least one edge that has not been traversed before the path is defined. For example, a set of independent paths for the flow graph illustrated now is path 1, 11, path 2, 1, 2, 3, 4, 5, 10, 1, 11, path 3, 1, 2, 3, 6, 8, 9, 10, 1, 11, path 4, 1, 2, 3, 6, 7, 9, 10, 1, 11. Note that each new path introduces a new edge. The path 1, 2, 3, 4, 5, 10, 1, 2, 3, 6, 8, 9, 10, 1, 11 is not considered to be an independent path because it is simply a combination of already specified paths and does not traverse any new edges. Path 1 through 4 constitute a basis set for the flow graph in this figure. That is, if you can design tests to force execution of these paths, that is basis set, every statement in the program will have been executed at least one time, and every condition will have been executed on its true and false sides. It should be noted that the basis set is not unique. In fact, a number of different basis sets can be derived for a given procedural design. How do you know how many paths to look for? The computation of cyclomatic complexity provides the answer. Cyclomatic complexity is a software metric that provides a quantitative measure of the logical complexity of a program. When used in the context of the basis path testing method, the value computed for cyclomatic complexity defines the number of independent paths in the basis set of a program and provides you with an upper bound for the number of tests that must be conducted to ensure that all statements have been executed at least once. Cyclomatic complexity has a foundation in graph theory and provides you with an extremely useful software metric. Complexity is computed in one of three ways. 1. The number of regions in the flow graph corresponds to the cyclomatic complexity. 2. Cyclomatic complexity V of G for a flow graph G is defined as V of G equal to E minus n plus 2, where E is the number of flow graph edges and n is the number of flow graph nodes. 3. Cyclomatic complexity V of G for a flow graph G is also defined as V of G equal to P plus 1, where P is the number of predicate nodes contained in the flow graph G. So if we are referring once more to the flow graph that we discussed earlier, the cyclomatic complexity can be computed using each of the algorithm just noted. The flow graph has 4 regions. Also, V of G, that flow graph consists of 11 edges and 9 nodes. So V of G can be 11 minus 9 plus 2 equal to 4. Again, through the third method, V of G, it has 3 predicate nodes. So V of G is equal to 3 predicate nodes plus 1 equal to 4. So in all these methods, we can identify the value of V of G that provide us with upper bound of the test cases. In this case, maximum 4 test cases can be defined for the given graph, so that it guarantees to cover all of the program statements executed at least once. The basis path testing method can be applied to a procedural design or to source code. In this session, we are presenting a basis path testing as a series of steps. The procedure is average, which is described through the set of program as shown here. It can be used as an example to illustrate each step in the test case design method. Note that average, although an extremely simple program, contains compound conditions and loops. The following steps can be applied to derive the basis set. Using the design or code as a foundation, draw a corresponding flow graph. A flow graph is created using the symbols and construction rules presented. A flow graph is created by numbering those PDL statements that will be mapped onto corresponding flow graph nodes. The corresponding flow graph is shown here. Second step of deriving test cases is determine the cyclomatic complexity of the resultant flow graph. V of G can be determined without developing a flow graph by counting all conditional statements in the PDL and adding 1. And thus V of G is equal to 6 regions, or with this flow graph, by counting the regions or by counting the edges and nodes or by counting the predicate nodes, we can compute cyclomatic complexity as 6. Third step for deriving test cases is determine a basis set of linearly independent paths. The value of Vg provides the upper bound on the number of linearly independent paths through the program control structure. In the case of procedure average, we expect to specify 6 paths. Path 1, 1, 2, 10, 11, 13. Path 2, 1, 2, 10, 12, 13. Path 3, 1, 2, 3, 10, 11, 13. Path 4, 1, 2, 3, 4, 5, 8, 9, 2, etc. etc. Path 5, 1, 2, 3, 4, 5, 6, 8, 9, 2, etc. Path 6, again 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, etc. The eclipse, etc., following path 4, 5, 6 indicates that any path through the remainder of the control structure is acceptable. It is often worthwhile to identify predicate nodes as an aid in the derivation of test cases. In this case, nodes 2, 3, 5, 6, and 10 are predicate nodes. The fourth step is preparing the test cases that will force execution of each path in the basis set. Data should be chosen so that conditions at the predicate nodes are appropriately set as each path is tested. Each test case is executed and compared to expected results. Once all test cases have been completed, the tester can be sure that all statements in the program have been executed at least once.